Doesn't want to understand.
Yeah.
Okay, without further ado, Clay Fox here, and now understand we're right at the same moment with Gerald Bennett is the next speaker from Kansas State, and the title of his talk is Understanding 71.
Yeah. Thank you very much, and thanks to the organizer to invite me here to Taipei, and it's a pleasure that I'm able to talk on Bob's 71st birthday conference. So my title is Understanding 71, and I will try to explain how 71 appears in mathematics. Yeah. There are two theorems in mathematics and physics where the 71 plays a prominent role. And the first theorem we talked already about is, I think Professor Harada mentioned this, that the largest prime divisor of the order of any sporadic group is 71. And I mean, this is a theorem which only very few people completely understand. People believe it is true. But there is another theorem where this number 71 here, and this is about self-dual or holomorphic vertex operator algebra of central sharp 24, namely we say that there are exactly 71. Now I should remark that theorem.
Most people believe that's true. What is your definition of the word theorem?
Yeah, I mean, theorem 2 is not yet completely proven, but we will know at the end of the week that there are at least 71 terms for that. That's the precise statement, and also after this talk, you should believe that this is the correct number. I mean, the theorem is a statement which is true, right? Okay, now let me start with contribution. So I think it was announced in 1980 and then finished in 1982. He showed that there exists 19688 three-dimensional algebra forming an irreducible representation for its automorphism group. And from this one can deduce the following two corollaries. So one is that the largest prime divisor of the order of any sporadic group is at least 71, and the other corollary is that the number of isomorphism clouds of self-dual vertex operator algebra central sharp 24 is at least 71. So let me say a little more how one deduces the corollary. So for the corollary 1, so if one has constructed the algebra and if n is its automorphism group, then one first has to show that it's finite. This was relatively hard originally, but now with the help of vertex operator algebra, this is better understood. Then one has to show it's simple, and from the construction it's very obvious that there is a subgroup 2 to the 1 plus 24 convex 1 in the monster, and then this was also very hard. One has to show that there exists an extra automorphism called the triality, which is not contained in this subgroup. Yeah, and then one observes that 19688 is is the product of these three primes. So one get in particular that 71 divides the order of the monster, and then finally this one has to use some finite group theory to show that this implies that the order of the monster is this big number, and therefore it's also sporadic group. And also has to show that really that this group is this order which is generated by sigma and 2 to the 1 of 24 conway 1, that this is a full automorphism group of the Griess algebra which was done by Gibbs. Now, if you have corollary 1, it's not then too hard to come to the proof of C of them 1, although better I shouldn't talk about this in this proof theory where I'm not an expert of. So what remains to be done is that one has to show that there are only 6 other sporadic groups besides the monster, and then one has to compute the orders and show that 71 is not a divisor. So let me nevertheless give you 2 slides saying a little about the last statement, because if one, this was mentioned already yesterday, if one just tries to do the odd order case, so to consider groups of odd order, this one can do now with a computer. Right? So there is now this machine check proof of the odd order theorem. So all what we have to do is we have to install proof assistant on your computer and load the 170,000 lines of code and let it run, and then it will say that your order theorem is true. Now I showed here some random part of the code. It doesn't mean that this is the right way to do it. I mean, it shows that mathematicians are able to give long proofs which are correct. Right? And on the other hand, you don't try to do this by hand. The computer should be able to do it by itself on papers. Anyway, for the second part of the proof of theorem 1, let me show you an example. So one has to show, if one takes one of the 6 sporadics not involved in the monster, that one can, that the order is not divisible by 71. So the way one can do this is one, I think this was in the paper, you define that S field is an element, then you write down 2 matrices, 7 times 7 matrices. You consider the matrix to generate by this 2 elements, and then you just can ask computer algorithm like magma, and it gives you the group order, and you can check what the composition factors are, and you can also do a computation like computing all exact groups, and the whole thing will take about a second or so.
So do those algorithms depend on the presentation? So do the algorithms of magma depend on the presentation?
On the
presentation.
No, what I think is magma is doing, it shows that this group is simple, and then of course it determines the composition factor computational, and then to identify the group, it looks at the group order.
How are you defining it? Generating relation?
Yes, I mean here. So there are 2 matrices, and you take the matrix and generate it by then by all matrix is generated by X and Y, and then
Yanko did this. Yanko.
yeah, of course, it was originally done by hand, right? Okay, but I don't talk about proof theory, but nevertheless, I also like to show you that one can do it for larger group, because this plays a role later for the second theorem. So if you do this for conway 0, this is harder because the group is larger. So what you can do is you can first define the Leach lattice, the laminated lattice, and then that gives the automorphism group. Now it's hard to compute with the 24 by 24 matrices because matrix multiplication still needs a lot of time, but it's better that you look at the include commutation action on the minimal vectors of the leaf spaces, and then you get a commutation action on around less than 200,000 elements, and then magma relatively quickly gives you the order, and it can also determine the composition factor with essentially simple, but if you try to do the all the subgroups, then it will time out. No, especially the problem with the memory. Nevertheless, we together with Jeff, we were able to solve a somewhat easier problem, and this was to classify all the fixed point lattices in the Leech lattices. So for this it was enough not to look at all subgroups of the Conway group, but only to look at those which are not two groups, and these we could classify. So the two group value seems to be between 10 to 100 million connectivity in that. Okay, now let's continue with vertex operator algebra. Yeah, so we have up to connectivity all the in fact, we're only doing it in the maximal subgroup to the 12 and 24, but this is the hardest one calculation. So there are about 80,000 or so non-two.
What's the non-two?
It's a subgroup which is not a two. So it has at least to have one other, they all have one other prime as well.
So you're just missing the zeros then?
Yeah, the two zeros are. Okay, now vertex algebra. So the construction of the Griess algebra was then extended by Borchardt and eventually Murman to a larger structure, which we call the vertex operator algebra. So we get the Moonshine module of central charge 24, and it turns out that it's the P2 part. This is the Griess algebra, and furthermore, the Moonshine module is also generated as a vertex operator algebra by the Griess algebra. So, in particular, we get that the automorphism group of the Moonshine module is also small. And the proof essentially is just an extension of the construction of P to vertex operator algebra. Now, it was shown by Chong-Yin-Gong that this vertex operator algebra is self-dual or holomorphic, so it means it has only one irreducible module up to isomorphism. And I think even before, in 1992, Charlatans considered the problem to find the genus of the Moonshine module, which means that one likes to find all vertex operator algebras of central charge 24, which are self-dual and up to isomorphism. And so what he found was, and what he constructed, was a list of 71 affine Kaczynski subvertex algebra. So this is the subvertex operator algebra generated by the degree 1 part of the vertex operator algebra. This is well understood, this affine Kaczynski vertex operator algebra, and he gave a list of 71. Now, progress has been slow, but as we will see at the end of this B, one can now prove that for each of these 71 possibilities for the affine Kaczynski sub-VOA, there is at least one such vertex operator algebra, and to say that the proof is drawn effort of many people. Of course, we need the construction of the Moonshine module, because it is one of those 71 vertex operator algebra, and then many people construct various examples of this delta-zero vertex operator algebra. I hope I haven't forgotten anyone. Now, already Shelton observed that the 71 which he found and the 71 in the order of the monster, that they are probably unrelated. But of course, it's still funny with the 71. Now, what I like to do in my talk, I mean, this was just an extended introduction so far, is to discuss if there is a deeper meaning behind the occurrence of 71 in both cases, and what I try to tell you is that although the cases are both unrelated, that there is a similar reason at the end why 71 occurs. So let me now first discuss the 71 and the prime divisors of the monster. So if you look at the ZP of prime divisor of the order of the monster, then it was already in 1974, before the monster was constructed, that these are exactly those primes for which the normalizer of gamma 0p is of genus 0, so this means that the corresponding Riemann surface has genus 0. Now, one direction, namely that if we have a prime divisor of the order of the monster, then that the normalizer has genus 0. This was explained by Borchers, who constructed out of this generalized Fluidity algebra and then the equivalent denominator identity of the monster Lie algebra resulted that the function had to be of genus 0. So this, the last step, this was later defined and simplified by Kamen and Gantt. Now, on the other hand, we don't understand yet conceptually why the monster realizes all the primes P, which has this, where gamma 0 P has this property. And so the only way I think that when one gets this prime, one has to use the Thomson order formula to get the order of the monster, or maybe one can now use Wilson's computer realization of the monster, although I'm unsure if one just uses this generator, if you can really compute the order of the monster without any various knowledge. Now, I also don't have any idea. So but what I want to talk now is about 4 possible explanations for the occurrence of the dimension of the Griess algebra, or the extended Griess algebra. In the Moonshine module, which is a transfer from a conformal field theory, we have always the energy stress tensor, and so that's the reason why we have to add here 1. Now, for the occurrence of 196884, this must be probably earlier. At least it was John McKay who realized that this number 196884 is the second coefficient of the elliptic J function. And now this occurrence we now well understand because the Moonshine module is a nice rational vertex operator algebra, and for such nice vertex operator algebra we know that the representation theory gives you a modular tensor category, and further this modular tensor category this defines then a representation of FL to Z, and the S matrix for this representation Griess is a character. Now in the case of the Moonshine module, there is only one module, and it turns out that one gets that the character of the Moonshine has to be a modular function. And since V1 is 0, I mean this fixed J or J minus definitely 744. This explains somehow the relation between the monster and the J function. Now, there are other ways where you can get the number 196884, which are not directly coming from modular form. So, there was Mathieu introduced the notion of what's called vertex operator algebras of class ST, which means that there is automorphism on the vertex operator algebra, that the fixed-point vertex operator algebra is very small, has large minimal weight, and I generalize this notion somewhat to the notion of conformal design, which is, works as an analog of the notion of block designs and spherical designs for in finite combinatorics and in lattice theory. And now what one has is that if one looks at conformal 8 vertex operator algebra, where the degree 2 part should form a conformal 8 design, and one assumes that the V1 part is 0, then what one gets is that the central charge of the vertex operator algebra has to be 24, and the dimension of the V2 part has to be 19884. Now, why does this number occur? The condition of a conformal design gives you certain relations between the dimension and the central charge, and these are the relation. And if you resolve it for integral dimension and rational central charge, then this turns out to be the only non-trivial solution. There are some other solutions, but they are more or less trivial. Second interpretation. Now, it's well known in combinatorics that the design problem and the packing problem, that they are dual to each other, and if you have a very nice object, then these two bounds, they usually have lower bounds for the design and upper bounds for the packing problem, that they coincide. And so this is true in particular for the big design, which comes from the Bode code, and for the minimal vectors in the Leech lattice, which form a spherical 11 design, but we also know there is a solution of the Kissing number problem in dimension 4. Now, so what would be the analog for vertex operator algebra? Yeah, I mean, you just like to make a certain part of the vertex operator algebra as large as possible. Now, if you like to take the Muncher model, we make. If we don't do this, we should say that V1 should be as large as possible, and then more or less we would get VK8. That is vertex operator algebra. So let's assume that V1 is 0, and then what we would expect is that the dimension of the degree 2 part is less than 19884, and that equality only holds for the Muncher model, because this somehow would be the dual bound from the design bound. And now I tried to work a little, and I hope that I will be able to boost the theory, but I couldn't do it, but at least I could get some partial result. So what we now this was from the modular tensor category description, is that the gradient dimension of the irreducible module of the vertex operator algebra, they are modular forms or modular functions for gamma n for certain length n. And in particular, they have to be non-negative since they count dimensions. Now, if we take the character of the vertex algebra and apply the S matrix to it, then this character is a linear combination of the characters of its module, so it also should have positive coefficients, and you can expand it then in power of q to the 1 over n, and now you have a linear programming problem which you can try to solve. Namely, the coefficients here have to be all positive, here they have to be all positive, and what you like to, I mean, this, the first coefficient has to be 0, and then you like to maximize this coefficient. And now, if you fix the level n, then you can let the computer do this linear programming problem, and I did this for few n, and it confirms it, so the larger power I could get. Now, for general n, I couldn't do it because the coefficients of this modular function go very quickly, so it became numerically unstable. And so what one needs is, one needs a better way to solve this infinite linear programming problem. Yeah, let me mention that this seems to be possible. There was, this year, it was opened by Griess that the Leech lattice is indeed the densest sphere packing in dimension 24, and similar with the E8 lattice gives the, yes?
It was known to Hoehn and Kumar that the Leech lattice was the densest lattice.
Yes.
So, did you mean Hoehn and Kumar or Hoehn?
No. What I'm saying is here, it's this was the Hoehn-1 support. This was the first paper where they used this linear. They gave a method to bound the latency. So they could already show that up to an epsilon, which was more or less numerically arbitrarily small, that the Leech lattice provides the densest packing up to 1 in part million, and then later Hoehn and Kumar, they showed indeed that this is enough, that the Leech lattice is the densest lattice packing, because this is somehow more discrete problem, and so it's enough to know this only up to a certain epsilon, but then finally to solve it, all what one had to do was write down a function with certain properties, but nobody knew this until she came up and used some quasi-modular forms for gamma 2. I still don't understand why this works, but it works. But the hope is that one could do something similar here for this sphere packing problem for vertical. And it's somewhat easier, since we only have to show that this dimension has to be less than 196.884.9, right? So then, because it has to be an integer. Okay, let me come to the fourth interpretation, and that's maybe the most meaning of all. So it was written, had the idea that one can use vertex operator algebras using the ADS-CFT correspondence to construct three-dimensional black hole. So somehow the eventual horizon of a three-dimensional black hole is described by such a CFT, and they actually bound by Bekenstein and Hawking for the amount of information a black hole can hold, and so now one can compare from using the numbers here in the Moonshine module with the Bekenstein-Hawking model. And so the observation of Wheaton was that if we take the logarithm of 196.883, then this is 12.19, and as you can see, this is approximately 4 pi. Yeah?
What